Yeah, so once again, good evening, all of you, and we are going to start today's session. And in this session, we will discuss about Euler method, Euler backward method. Okay, and by using the same, we will discuss some examples which are related to in health science and engineering. Okay, so start the before starting the session, I have to share the screen and then we will discuss one by one. So okay, and there is one more file. Okay, just 1 minute, please. LaTeX file. Where is LaTeX file? Okay, this is the file. Yes, so this is the main overview about the method which we are going to discuss today is the backward Euler method, and this is also is based on the numerical technique used for solving ordinary differential equations and partial differential equations also. Okay, we can use this method for both type of equations, whether it is a ordinary differential equation or partial differential equations, and it belongs to the family of implicit method, meaning that it involves solving the equation involving the unknown values at the next time step. Okay, and making it particularly suitable for stiff ODE or PDE. So before starting, I would like to ask from you, what do you mean by stiff ODE or PDE questions? Anyone can let me know what are the stiff type of problems? Anyone, please? Which type of the problems are known as stiff problems? Can you please explain, anyone? Okay, no problem. We will discuss in the detail with the example. Okay. So here are some key features of the backward Euler method. This file I will also upload for you, and I will try to share in the WhatsApp group. Okay. So unlike explicit method, the backward Euler method involves an implicit formulation, and it computes the solutions at the next time step by solving an equation that include the values of the unknown at that future time, and time discretization domain, breaking it into discrete time steps. The backward Euler scheme update the solution at each time step using the information from the current and the future time points. Okay, and what about the stability of this method? One of the advantages of the backward Euler method is its unconditional stability for linear problems. This is very important. This makes it particularly suitable for stiff ODE or PDE, where explicit method might require very small time steps to maintain the stability. But in this case, this will maintain automatically. And implicit equation, which is required to use for this method. Okay, so the implicit equation in the backward Euler method is typically solved using iterative method like Newton's method, which we discussed. This step involves solving a nonlinear algebraic equation for the unknown values at the next step. And application areas we know very well. So this is the basic idea about this one. Okay, see, this is the basic idea about to use this method. So when we have the dy upon dx, dy upon dt is equal to ft y, where y is unknown at the time t. The backward Euler method discretizes the time domain into discrete step, and the basic idea is to approximate the derivative using backward difference. So the difference which we will choose will be backward. Okay. So as you know, if we have at this place Tn, and here is Tn plus 1, and here is Tn minus 1. Okay. So in the your normal Euler method, we use this technique. So delta Tn was equal to delta Tn plus 1 minus Tn. Okay, but in the case of this one backward, we will take the difference, this one, Tn minus Tn minus 1. So this is the main difference between these two. So this type is known as, by using this difference, we have the backward difference. Okay, so by following this one, we are using discretization. And you know Tn will be equal to T naught plus NH. Okay, and the backward Euler formula is, you can observe at this place very clearly, yn plus 1 is equal to yn plus h f tn plus 1 and yn plus 1. Okay, so this equation will be used, and this is the implicit equation because yn plus 1, see at its place, yn plus 1 appears on the both sides, see here, on the left hand side as well as on the right hand side. So it is typically solved using iterative method such as Newton's method. Okay, so we can have the approach which we will apply. So this is similar thing. One more thing which I want to explain before starting this method. Here is one more file. Yes, see here. Okay, so the forward Euler is just, we have the Euler's method which we have already discussed, and the backward Euler is implicit, also known as implicit Euler. Okay, and see in this case, when we discuss the Euler forward or Euler method, that is in this form, yn is equal to yn minus 1 and plus delta t and f t n minus 1 yn minus 1, which we have already discussed in the very first method. Okay, and now we have the method is at this place. Along with we need to discuss here the stiffness. Okay, so this is the formula you can see in this equation. Yn is equal to yn minus 1 plus delta t and f t and yn, and here yn appears on both sides, left side and on the right hand side. Okay, this is the formula, but we need to discuss here stiffness, and also in this case the slope will be taken from the future point Tn Vn. Okay, but in the case of forward we are taking from the previous point, but here from the current point, but here we are taking from future point. Okay, so you need to compare the difference between these two. And what about stiffness? Here is one diagram which I want to use. Here is one diagram. Okay, here was the diagram. Just 1 minute. Yes, you can see this one. You can see this one. When we have the solution in this type, and 1 minute please, I want to open my Epic pen. Yes, okay, see in this case, yes, see in this case from this interval to this one. Okay, so we need the change in this graph is very frequently, or very big change in the graph from this point to this point. So to get a more accurate solution, we have to divide this interval in very small step size to get more accurate solution. But after this one, the graph is smooth. Okay, so in this part we can choose large step. Okay, so that's why when we are using forward Euler method or Euler, so this problem is occur, and to make more accurate, what we need, we have to divide this entire interval in very small step size. Okay, and this is the problem of stiffness. Stiffness means in the big change in the small step in the graph. Okay, so here from this interval to this interval, you can observe easily there is big change in the graph, but after that we have small change in the graph. Okay, so for the stability of this part in which I highlighted at this place, we have to take very small step sizes, as you can see. But after that, the graph is you can say smooth, and we can take large step. Okay, here you can see the you can compare the step size for this interval to and the other. Okay, here we have very small step sizes, and we need these small steps due to stiffness. Okay, so the stiffness is the large change or big change in very small steps. Okay, so for the stability of this type of solution, we can easily use this Euler backward. So by using this one, we have a stable solution, this type of problem. Okay, and so this is about the stiffness. Now, how we can implement this method? This is important. Come here in the MATLAB. Come to the MATLAB, and also we need this part also. Just 1 minute backward, and you can use. Okay. So the to check the stability region, we are given this equation yn is equal to yn minus 1 plus delta t yn. Okay, and yn will be equal to yn minus 1 upon 1 plus lambda delta t, and 1 upon 1 minus lambda delta t is the amplification factor for backward Euler. Okay, and in the case of forward, we have 1 plus lambda delta t. So sometimes this yn is equal to yn minus 1 upon 1 minus lambda delta t. This will help us to convert any problem to implement backward Euler method. Okay, so we need to keep in mind both type of the expressions so that we can easily convert and we can use one of these two equations. So now we can come to the MATLAB. Yeah. So here we have is, yes, we need to create a function for backward Euler, and suppose that we are given the differential equation is dy upon dt is equal to fty, and the time span we have is t naught to tf. T naught is the initial and tf is the final. Okay, rest other are, we have the same initial condition, a number of point outputs, we need t and y. Okay, so these are the output functions, and now we can easily implement, and some of the steps will be similar as we do for the others. Okay, so here is the complete program. Okay, so see here, this is the t naught, the initial point of the interval. Okay, and this is the last point of the interval, t naught to tf. Tf means final point, and we can calculate the h value of final point minus initial point upon n, and line space of t we can easily generate by using line space function, and y zeros, you know, the length of t arrays and y arrays must be equal, only then our graph will be plotted. Okay, and this is the initial value. Okay, so at this place we are initializing the given condition. So this will be y1 is equal to y0. Okay, this is the first index. So we are using at this place backward Euler iteration, and I will be start from 2. Okay, one index we are using at this place, so we have to start the index from 2. Okay, then we have ti and yi is equal to I minus 1. And then after we have the equation, you can see at the place in the MATLAB syntax, which we discussed just now. But to solve this problem, we are using fsolve function. Here is the function which is fsolve. So what this equation will, this function will do, this will solve the differential equation for which value we need. Okay, so here you can easily write at the rate, you can see at the rate y next. Okay, so the next point is the function of which one? One is y next. Okay, and then minus yi. So how you can write this one? How you can write? See, you will take this entire right part on the left hand side. So you can easily convert. At this place we are getting the y next minus, this will be minus y I, then minus h, and f ti y next. Okay, so this is the next value. You know, this and this both are equal. This and this both are equal due to this expression. Okay, so this is the entire differential equation, this one, and you can see at this place comma. Okay, and we want to solve this differential equation for what? Yi. We want to solve for yi. Okay, so whatever you will put at this place, that value will be computed, and after computing, the entire value will be stored at this place. So this is the entire program of this Euler backward method. But the only thing which you need to keep in mind, how you can convert this equation and the equations which I have shown you on the PDF file. Okay, just you need to convert the equations in this format, and you will use fsolve function. This is inbuilt function in the MATLAB. Okay, and by using fsolve function, you can solve system of equations, you can solve system of differential equations. Okay, and you can solve like any polynomial by using this function. Okay, in the detail we can discuss in the coming sessions, but here due to lack of time, I did not introduce more detail about this f function, but we have to put the differential equation at this place and comma yi. So this value will be calculated from this expression or this differential equation, and the value will be stored on the left hand side. Okay, so all the values which will be computed corresponding to the index which we are providing here, I equal to 2 to n plus 1 will be stored at this place, and then we can use this function, this program, to find the solution of a differential equation. Okay, so here we have the numerical values. Come back on the next here. Yes, okay. So here we have, this is, okay, so here we have, this is the ODE. F is equal to @ty minus ky. Okay, so the differential equation we have is dy upon dt is equal to minus ky. We want to find out the solution of this equation, and the value of k is 0.1 and t span is 0 to 10, and y naught is equal to 1, and the value, that of value for number of step we have is 100. Okay, and at this place we will call the backward Euler method, which we just create at this place, and we are calling the function at this place. Okay, and the file we have saved in the same directory, you can see, and the all the input arguments which are required has been assigned in the above statements. Okay, and after that we have the plot function, and you can assign the other x label, y label, whatever we need. Okay, see here. So this is the plot function, x label, y label, title, and grid on. Okay, and when you will execute, and you can see we have, this is the solution. Okay, and 0 to 10, and on the vertical line you can see the solution of y. Okay, so there are two variables, one is t on the horizontal line and y on the vertical line. Okay, so in this way you can use, and I also just now I came to mind that you must compare both the solutions using this backward Euler method as well as with the Euler method which we discussed in the last lecture. Okay, so you must compare these two. I did not include the comparison between these two, but you must compare and find the error, which method is more suitable. Okay, you must try. So this is all about backward Euler method. If there is any question related to this discussion, please feel free to ask from me. Yes, please, any question? Any question, please?
No, sir.
Okay, thank you. Okay, so this is about this example which I try to discuss with you, and now we have I include various examples here. Okay, this is the next example, and also one more thing I will let you know. When you will execute all these functions, okay, you have on the you can see in command window, there are some detail about the computing of backward Euler method. Okay, you must go through about all these detail which you can see in command window. This will help you for more understanding about the method. Okay, so now once again I am opening the next example. So once you will write the program, then you can take various type of examples. And here is one more example. This is the same process. You can say f solo function is there, and you can these are the same step, but the expression are a little bit different. Okay, so here we are using y. Okay, so at the place we have y, and this is the y previous. So we want to solve this equation for y I previous. You can see at the place comma. Okay, you can see at the place comma, and we want to solve this value. But keep in mind how the expression I change. Okay, compare the previous example as well as the equations which are in the form of iteration or the PDF file, how we are converting these equations. Okay, the only thing in all the methods is that this part, only this part. The other all the other things where you are applying for initial conditions, line space. Okay, these are similar in all the methods, and also all these will help you in PDE. Okay, or higher order. Okay, so all these are similar. And here is also we have one more example. We have added space is minus 0.1y, and the value of k is at the place. Okay, and when you will execute, similar type of solution we have. You can check. I will provide all the codes of the other examples, example number 4 and example number 3. Okay, so these are same type of examples, not much more difference. Okay, but only the syntax in a different way are used, but method will be remain same. You will try all these files, and when you will write the code in different way, this will create computing thinking. So here we are going to discuss the engineering problem. This is the application part, and will very helpful for you how you can easily implement. So the backward Euler method is a numerically technique commonly used to solve ordinary differential equations. And in engineering, it finds application in various fields such as control system and structural analysis, circuit simulation, fluid dynamic, and others also. Okay, so here we are going to discuss how we can use or apply backward Euler method to solve engineering problems, and we choose at the place very simple and interesting example. So formulation, start by formatting the engineering problem as an ordinary differential equation. If you are dealing with the simple first order, you can see resistor capacitor circuit we are choosing at the place. So this is the corresponding equation. RC product dV upon dt plus V is equal to V in. Okay, where V is the voltage across the capacitor, and Vn is the input voltage, R is the resistance, and C is the capacitance. Okay, so our main objective is you need to convert this equation in the form of ODE, and then we can easily apply the backward Euler method. Okay, and I try to explain everything at this place, how you can convert and how you can use. So here you can find the complete process. So the parameters which we need to assign the values, we can change. The value of R is we are choosing at the place 1, that of C is 1, and input voltage we have is also 1, and T is the total simulation time. Okay, and H is the step size, and the number of time steps if you want to calculate, that will be N equal to T by H. And after that, initialize the arrays, and the solution will be it will include V and T. Okay, V will depend upon T, so the length of these both must be same. So we are using the 0 vector. Okay, so 1 to n plus 1, and T is also 1 to n plus 1. Now we are going to apply the initial condition. Okay, so this is the initial condition. And now we are using at this place backward Euler method, and Tn plus 1 will be equal to Tn plus h. And now see this equation, Vn plus 1 is equal to Vn plus h Vin, okay, upon 1 plus hr product C. Okay, just 1 minute. See this equation. Yn is equal to yn minus 1 upon 1 minus lambda delta t. This equation is used. Okay, so that's why I told you that you must have these two expressions. Sometimes we are using this one, and sometimes you are using this one. Okay, so now by using the same, and we have the plot, rest all the statements are same. Here we have the plot function, x label, y label, title, grid on. Okay, so when you will execute this section, okay, so this is different type of the file. We divide this script file in the slices, okay, in section wise, and just you need to run only this content section. So for that you need to press at this place, and you can have the solution on the horizontal line. You can see the time, and on the vertical line we have voltage. Okay, and you can see from 0 to 5. At the 5 we have the maximum value voltage is about 1. Okay, and at the 0 we have 0. So this is the solution of this equation. And after that there is analysis part is also I try to include. This will help you. So this is the basic example to use. There are so many problems in engineering where we can use this method for control theory, for circuit, and many more examples are there. And there are so many stiff problems are also there. Okay, and here we have one more example related to health science. Okay, you can see when you will apply this method, these will appear always. Here is one example in health science. Okay, the backward Euler method is numerical technique used to solve ODE. In health science, ODE are often employed to model biological systems such as drug kinetic, population dynamics, or disease spread. Okay, so here simple example of how you might apply the backward Euler method to solve a health science problem by using MATLAB. Okay, so here you can see the model which we are choosing at this place. Let's consider a basic pharmacokinetic model describing the concentration of a drug in the bloodstream over time. The model can be represented by the following first order equation: dc upon dt is equal to minus kc, where c is the concentration of the drug in the bloodstream, k is the elimination rate constant, and we want to numerically solve the ODE to find the concentration of the drug over time using a backward Euler method. So the process is very quite simple. Just we need this equation and corresponding to the initial condition and the value of C and K. Okay, and we can easily implement the same. So you can see the parameters which we required, K 0.1. and t, the total simulation time is 10, and dt is equal to 0.1, which is the time step. Sometimes we are using h and we can use dt. Okay, so dt is also the step size, and the number of steps if you want to compute, that will be t upon delta t or dt. Okay, so this will return the number of steps, and the initial condition C naught is equal to 100, and after that you know we need the arrays to store the results. Okay, this is the time array, and this is the C, and this is the initial condition, and after that we are applying the same backward Euler method in second equation. Okay, second format we are using this one, yn is equal to yn minus 1 upon 1 minus lambda delta t. Okay, so the other statements are same. To plot the graph, plot time c underscore be, then we have marker blue color hyphen, line width we are using 2. X label is there, Y label is there, title and grid down. When you will execute this sequence of statement, and you will find, okay, so this is the corresponding graph of our corresponding to our inputs, and the function and the program which we write for the required program. Okay, and everything is fine. So these two examples I try to include at the space, and some more explanation I try to introduce here. This will help you for more understanding. So there are so many problems in health science and in engineering, in physical sciences, where we can use this method. Okay, the other methods are also there, but depends upon the stiffness in the equation. If exists, then we can use this one. So you can see that the number of steps we are not required to change. Okay, and if you will use other methods, then you need to decrease the step size. So this is all about this today's method, and I hope that this will help you to apply in different type of problems for your study. Thank you very much. So this is all about today's session. If you have any more question, please, over to you now.
Sir, good evening, sir.
Very good evening, sir.
Sir, how the stiffness came in that dc by dt equal to like concentration problem, sir? That drugs concentration problem.
Only stiffness is mainly when the results are changing, are not stable sometimes. Okay, and there are some problems where the results are similar as you are using Euler method or backward Euler method. Okay, but sometimes if the solution is changing very frequently in the some particular interval, and then have a smooth, in that case we have to apply for the stability this backward Euler method. Okay, so all these concept will be clear if in the beginning I told you that I did not introduce the comparison between these two methods. So the thing is how much we are doing the experiment, and by doing the experiment for the different problems, and when we have the comparison, then this will help you for the more understanding. But in this case, I think when you will use Euler method, you must try, but I did not compare the result. This is the missing part from my side. Okay, so you can apply the Euler method also for these examples. But if there is stiffness, then this backward Euler method will be more suitable for the stability of the solution.
Okay, sir. Thank you, sir.
Okay. Yes. Any more question, please? Actually, the thing is that there are several methods. Okay, and sometimes we ourselves are also confused which method is more suitable. So the thing is, corresponding to each method, there are some conditions, their accuracy which we are using, and also you check the stability of each method. Okay, and we must compare with each other. By comparison, the concept will be more clear. Okay, stability, errors, and by finding the stability and error analysis, all these methods will be more understandable, which method is more suitable. Okay, sometimes the simple method, just like Euler, is more suitable if there is no stiffness. Okay, and we can take large step, and we have, because when we have the large step, times we can save the time also and reduce the complexity. But sometimes just like in the case of stiffness, in the case of stiffness, what is there? There is only one particular interval, sub interval, where the stiffness is occur. Okay, that's why we are using backward Euler method. Okay, But if there is no stiffness in the equation, then why we should use this method? We can use Euler method, and we can use Rangikuta method. Okay, both have more accuracy.
Sir,
And
excuse me,
yes, please.
sir. Uh, uh, Sir, can we say like this? Because sir, this backward Euler method is the implicit method. That is the
Yeah.
unconditionally stable method, sir. So it can be applied for any h step size, because if it will change in the step size h in any interval, so it will not affect on the stability. Like it will not affect our solutions, because if you will increase or decrease the step size, so the solution will be not unstable, sir. We can say.
Might be.
Because sir, it does not depend upon the h, because that is unconditionally stable, this method.
Yes, yes, yes. Any more question? So the content which we discuss here will be uploaded, and the PDF files will be shared in the WhatsApp group also. Okay. Tomorrow we will start the session at the same time. So if you don't have more question, we can end the today's session.
Thank you, sir.
Thank you. Thank you all of you.
Thank you.
Thank you. Good night.
Good night, sir.
Good night, sir. Good night, sir. May I call you, sir?
Good night. Good night.